Hello everyone, this is week 2 of our Intelligent Agents in Learning Environments course, and today we are continuing with Python and neutral nets. Today we're going to be talking about gradient descent and cost function, generalization in neural networks, and Kolmogorov-Arnold networks, also known as CANs. First, we're going to cover gradient descent and cost function. Gradient descent is an algorithm that minimizes the cost function by adjusting the input values to change the weights and biases, and its main goal is to improve the program's performance on a given set of training data. After training the network, it will be given a new set of data it has not trained on before and it has not seen before, and it should have a higher accuracy when classifying these new images. As we learned in the previous week, each neuron in a neural network is connected to all neurons in previous layers, and the weights and weighted sums of the activations are the strengths of those connections. The biases determine whether the neurons are activated or not. The cost function in a gradient descent is a measure that tells a computer how bad it is performing by taking the weights and biases of that neural network as inputs and returning an output result that shows how incorrect they are. And this is calculated by adding up the squares of the differences between the actual output activations and the expected output values. We adjust these inputs by shifting the input in the opposite direction of the slope, meaning that if the slope is positive, you shift the input to the left, or if it's negative, you shift it to the right. This is repeated until a minimum of the cost function is reached, which means that the performance of the program should improve. Next, we're going to be talking about a neural network's generalization ability. A program's ability to generalize comes from its ability to perform on new data instead of data it has already seen or trained on. Ava Amini is a lecturer at MIT, and she uses an example from a previous paper where they took images from a large-scale dataset and put class labels on them. In the image on the bottom left, you can see a visualization of this example. Then, they randomized the labels on each picture by using a die with k sides, where k represents the number of possible classes in a dataset, and assigned the images a new class based on the outcome of the rolled dice. Then, they used the dataset with incorrect labels as training for a new neural network model. They discovered that as you increase the randomness in the labels, the accuracy of the program when used on a test dataset with its original and accurate labels drops drastically. However, when they looked at the accuracy of the training dataset, they found that regardless of the randomization, the program's accuracy was still very high, as we can see in the image on the bottom right. This shows us that a powerful neural network can effectively fit the training data, no matter how randomized or incorrect it is. In Dr. Hassabis' interview about accelerating scientific discovery with AI, he makes a similar statement towards the end of his interview. He states that the modern computers can do much more than we previously thought because of the massive amount of pre-computing that they do ahead of time, and then use it to develop a good model. You can then use that model to efficiently solve solution space in polynomial time. He uses a similar example at the beginning of his interview with his company's own model. Dr. Demis Hassabis is the current CEO of Google DeepMind, which is based in London. He first became interested in artificial intelligence at the age of 4 when he began to learn how to play chess, which then led him to coding his first AI chess program at the age of 11. Games became important to DeepMind's early work. They used games as a proving point for artificial intelligence because it was easy to create data and define objectives that the system should complete. For example, Go is a strategy board game where your goal is to get more territory than your opponent. The game is so complex that there are over 10 to the power of 170 possible positions, which is more than the number of atoms in the universe, which makes it impossible to code a brute force solution to win the game. However, the company had a big success in 2016 when its AlphaGo program managed to beat the world champion at the time in a game of Go. Not only did the program win the match, but it also came up with strategies and ideas that had never been seen before, ever since the game was first created. This was possible because AlphaGo and its other successor programs mastered not only Go, but other two-player games as well through self-learning, where the systems go against each other to learn strategies instead of being directly hard-coded within them. This goes with his statement at the end of his interview, because AlphaGo previously pre-computed from repetitively playing games of Go and learning other two-player games, which trained it well enough to efficiently find a series of strategies to beat a real person. Lastly, we will be talking about the Kolmogorov-Arnold networks, also known as CANs. These are neural networks where the activation functions are trained instead of the weights of the neurons. These networks are based on the Kolmogorov-Arnold theorem in mathematics, where continuous functions can be represented by mostly addition. Remember, neural networks have an input layer, an output layer, and hidden layers in between, where all neurons are connected to every neuron in the previous layer. Kolmogorov-Arnold networks are similar. They have the same layers and connections. However, the main difference is that regular neuron networks have a fixed activation function, where you decide what they are beforehand and you just train the weights to find the set of ideal numbers to model your data. But in the Kolmogorov-Arnold networks, we have fixed weights with a value of 1, and instead we train the activation functions where you find the perfect function that will help to model your data as seen in the image on the bottom right. When training a regular neural network, you start at any input for the weight, and based on its output, you use gradient descent to shift that weight until you reach an optimal minimum of the function like we covered earlier. In the CANs, we still start with any input for the weight, but we change the activation function that is used to shift it until it reaches an optimal minimum of the function as well. However, it is hard to train functions because they have too many parameters, so we are going to simplify and express these functions to only a few parameters by using B-splines. B-splines are functions that we can add to approximate a function. There are different kinds of B-splines, such as constant, linear, and quadratic B-splines. Constant B-splines divide intervals into smaller sections and assign a constant value to it. While linear B-splines are similar, the sum of all the segments should represent a linear piecewise function, and a quadratic B-spline uses quadratic functions to assign values. These functions are then used in notations where the weights of the splines are multiplied by a certain number, which is the knot vector, and then the splines are connected with edges to the neurons, and the weights of the knot vectors are recorded as the new weights as seen in the image on the right, which then ultimately trains the function instead of the weights in the Kolmogorov-Arnold networks. Thank you for watching.